Hello, my name is Yili Zhao. I'm working on the Habitat Simulator at Facebook AI Research. The Habitat Simulator is a highly efficient photorealistic 3D simulator developed to facilitate that embodied AI research. It's quite fast. For example, it can render a scene from the multiple 3D dataset in a couple of thousand frames per second in a single thread. This tutorial intends to teach you how to use our simulator to do the navigation by a series of coding examples. Before we start, I would like to introduce a few important concepts in our simulator. The first one is the embodied agent. This is a virtual intelligent agent that interacts with our environment. Once we have the agent, we can define a sensor. This is a device that is attached to the agent, so the agent senses the whole world using the sensors. We can put an agent into the scene. The scene is a virtual 3D environment that contains the agent, contains a lot of objects, static, dynamics. Once we have the scene, we have to manage it. So we introduce the concept called the scene graph. This is the core data structure within our simulator. So it looks like a tree, which organizes logical and often spatial representation of the scene. In this tutorial, we hide it under the hood, so probably you will not manipulate it directly. But we still decided to introduce this concept here because you will see this in many places in the following tutorials. The last concept is, of course, the simulator. It collects all the concepts I just talked about, and it's a driver to time-step the entire simulation. Let's start. The first two sections are just to set up the collab environment, so we can quickly go through them. The third section, we define the utility function to help us display the sensor observations in the following chapters. In the first example, we call it Hello World, meaning this is the simplest program to demonstrate how to use our simulator. First, we need to write some specifications. It will describe the scene we are going to load, and specify the default agent and list a couple of sensor parameters, such as the relative position to the agent. For example, here, we set the height of sensors in meters, and the resolution of the observation. Once we have the specification, we can create a configuration that can be understood by our simulator. We do this job by defining a function called makeSymbolConfig. This configuration consists of two parts. One is for the simulator backend, and the other one is for the agent. You can attach a couple of sensors to the agent. For example, here, we attach only one sensor called RGB visual sensor to the agent. We specify its name, the sensor type, the resolution, and the relative position. Here, in this piece of code, and we pass it to the agent. We use this to form a configuration for the simulator. Let's execute it. Once we have the configuration, we can initialize our simulator backend. If you see this message, it succeeded. Load the simulator to the backend. It's very interesting that you will see that we load a Nav Mesh. The Nav Mesh is a very important concept that we will introduce in the following chapters. But for the first example, you can safely ignore it. Once you have the simulator, it's the time to initialize the agent. We pick up the default agent. We can set the agent state. For example, we can set its location in the world space here. We can also query the state. Let's execute it. So it tells me currently the position of that agent and the rotation expressed in the quaternion. Once we set up the agent, we can put it in the scene and let it to walk around and see. To do this, we predefine the discrete action space. This space contains 3 actions: move forward, turn left, and turn right. User, of course, you can customize this discrete action space, and of course, you can define your own. We will show you how to do this in the following chapters. Here, we ask the agents to turn right twice and then move forward and turn left. We define a function called navigate and see. So in this function, it will display which action the agent is taking and then display the observations from the sensor. Let's see what will happen. See here, we see 4 images that return from the RGB sensor. That's it. That's all for the first example. In the first example, we have shown you how to load the scene, how to set up agent with a sensor, instruct the agent to navigate and see and obtain observations. In the following section, my colleagues will present a more complex example to demonstrate the usage of different types of sensors, such as semantic sensor and the depth sensor. And we are going to show you the different observations from these sensors. We will also introduce the semantic scene and its annotation. We'll also teach you how to define and configure the action space. Thank you.
Hello, my name is Gokaslan. Today I'm going to teach you how to take your dragon or your agent for a random walk. To do this, we need to define a couple things about our simulator. First, what room we're going to be in. It's going to be this testing room, which contains both the mesh and the semantic information about the house that we're going to be exploring. We also need to find the observation space and the action space of our agent. So we're going to do that here. We're going to give it all, we can give it 1 or more of these sensors. In this case, for this tutorial, we're going to give it all 3, and you can toggle them with these little check marks here. Then we're going to create this sim settings dictionary here, which is going to have the some attributes which we will reuse later in the tutorial. So for the sensors particularly, we need to define the resolution of the sensor, the width and the height, as well as where it is on the agent. In this case, it will be 1.5 meters off the ground and directly at the origin. We're going to store our test scene for later use. We're also going to say our default agent is 0. Note we can have multiple agent configurations, so we're going to just have the 0th index be our primary agent, and we're going to store the Boolean values about whether we actually want to use the sensor. We're also going to set a pseudo random number generator seed, and we're going to decide if we want to enable physics or not. We will not enable physics for this part of the tutorial. If you want to learn more about physics, please check out some of our other tutorials like interactivity and advanced features. We're going to define a make configuration object here, which is going to have the various settings that are for the global simulator as well as our particular agent. It's going to ingest this dictionary that we defined. It's going to create a simulator configuration, which is the global settings I mentioned earlier, which is going to be what GPU device it's running on, 0 since we only have 1 GPU, what the mesh scene is, and whether physics is enabled. Note that physics is not enabled by default, but if this flag was to be true, you could enable it. Would just be that easy to enable. Now, we have this dictionary of sensors, which is going to be populated from values in that simulator dictionary we defined previously. It's going to store resolution and the position of our sensors, which are the same for all 3, as well as the sensor type for each, which will be color, depth, and semantic. Now, if our sim settings config dictionary has these Boolean values to be set to be true, color, depth, and semantic, we're going to create a sensor specification for that sensor. We're going to set the UUID to the key, which is going to uniquely identify the sensor. And we're going to set the sensor type and resolution and position, and then finally append them to a list. Now we have all these sensor specifications, but what do we do with them? We have to attach them to something. So that's where our agent configuration comes in. We create one. We're going to set give the agent all the sensors we just defined. And we've now created the scene, what the agent can see. The question is, what can the agent actually do? And that's where this action space comes in. It will be a dictionary that has keys and values: move forward, turn left, and turn right. The value will be an action specification, which is going to just call it's going to call some defaults we have in Habitat Sim, move forward, and we want to move forward by 0.25 meters. It's now going to also be able to turn left by 30 degrees and turn right by 30 degrees. Now we just have to take all these together. We're going to create a global habitat configuration object, which will have our simulator configuration here, as well as a list of agent configurations. Each agent configuration will define an agent. You can have multiple of them because we have support for multiple agents. Now we're going to run that function we just defined and instantiate the simulator with our configuration object. Now we've loaded the scene. As you can see, the Nav Mesh has been loaded. We're going to go and actually get the semantic scene object and see what's actually around in our house. Each house is going to we're going to print out what's in the scene. Our house is going to have some number of floors, some number of rooms, and some number of objects in those rooms. It's going to have a access aligned bounding box center as well as sizes. Each scene is we're going to loop through those floors, get the ID for each, and print them out, as well as the AAB center and the AAB sizes. We're also going to do the same for each region, which will be a room, and each room will have like a category name. So a kitchen, a bedroom, as well as a unique ID. And we even have that for each object level. So we'll know what the chairs are, what the bed is, and so on, and we'll to visualize that with the semantic sensor output. We're only going to print out 10 of these because it takes up a lot of space. But let's just run that and see and look what we have. So we have 10 rooms with 187 objects over one floor. This is the bounding box of the house, which the bounding box is defined is an axis-aligned bounding box, so it's defined by the center and each dimension of the bounding box, which is going to be like the height, width, and length. And we have a region here with a bedroom that has a wall, a curtain, a bed, a TV monitor, and so forth in it. Now let's create our agent so we can go and actually see what the scene looks like. So we're going to set our random seed and our simulator seed to that seed value we have from our original sim settings dictionary. And now we get to initialize the agent. We're going to initialize the default agent, which will be 0. And then we're going to go and set the agent state to this value. You can set the agent state to lots of different values, but not all of them will be navigable, and 0, 0 will not always even be in the even in the room mesh or the house mesh. Note that we're going to talk in the later part of the tutorial about how to sample navigable points, which are positions you can actually get to, and set the agent to one of those. But for now, we're just going to hard code it, and we're going to print out it to make sure it actually moved. As you can see, it's where we expect it, and there's no rotation applied, so all is good. Finally, we can actually do what we set out to do initially, which is to randomly walk our agent, to select a random action and have our agent take that action. So we're going to list all the actions we have, all the actions that exist for the default agent, and we're going to do it for 5 frames. We're going to randomly pick an action from this list, print it out, take a step in our simulator, and list all the observations for the RGB semantic and depth, and display them. And we have RGB, our semantic, and depth information. Now note that these are instance level semantic information, so if you wanted to simplify the category, you'd have to use that ID to category mapping we previously defined. On the pixels, it'll just be a simple NumPy operation. And now that we've But as you can see, we have all the RGB data, the semantic data, and the depth data, and we picked actions at random. And that is how you take your agent for a random walk. I hope you've enjoyed my brief tutorial into randomly walking your agent, and thanks for watching. Once again, my name is Gokaslan, and I'm now handing it over to Alex to talk about working with the Nav Mesh.
I'm Alexander Clegg, and in this section, I'll talk about working with the Nav Mesh. So why do we need the Nav Mesh? In previous sections, we took advantage of kind of the automatic response of Habitat Sim, loading this navigation mesh from file, and handling the navigation constraints under the hood. In this section, we'll talk about exactly how that is implemented and how to mess with that mechanism. Essentially, it's a light, fast mechanism for enforcing navigability constraints. So where is the agent allowed to be in the scene? We provide this functionality through recast navigation and detour in the nav module. And in this section, we'll demonstrate loading, recomputing, and saving the nav mesh, as well as some of the utility functions for visualization. So what exactly is the nav mesh? It's a polygon mesh, a 2D mesh embedded in 3D, as you can see in this image, where we are approximating the agent as a cylinder, and then we're computing all the possible locations in the scene that that agent could sit. And this is done by voxelizing the scene, and then building a height map on top of that voxelization in the gravity direction, and then building a nice detail mesh on top of that to make pathfinding pretty quick and efficient. So let's talk a little bit about some Nav Mesh utilities. First, and maybe most convenient, is to build a top-down map. And we can do this directly from the Habitat Sim API, from the Pathfinder module, or we can do this from the Habitat Labs Maps module, and we'll talk a little bit about both. Before we do this, remember that this Nav Mesh is actually embedded in 3D. So to get a top-down map, we're going to have to specify a particular slice, horizontal slice, which we want to visualize. So that's what this height parameter is. And this is going to visualize the nav mesh within a half meter of slack. So here we have the cell. We're going to define a couple of functions to convert 3D points to 2D points on the map, and to display the map with Matplotlib. Then we're going to define the resolution of our map in meters to pixel, and the height of our map. And right now, we have this toggle over here to do custom height, so if you want to play with it, you can. If we untoggle this, then we're going to set this to the scene lower limit. So we can get this from Pathfinder get bounds, and just grab the minimum Y value for that. Then if our Pathfinder is loaded, so we can actually build a map of something, then we simply grab that from the Pathfinder get top-down view function. Alternatively, if you want to go through the Maps module in Habitat Labs, then you can simply call maps.get top-down map, and you'll have to import maps to get this. So if we run this cell, we'll get a couple of outputs. First, we're printing out the nav mesh bounds, so you can see what that bounding box is going to be. And then we're displaying the map at this minimum Y coordinate. So this one is coming straight out of the Pathfinder API. And then we have this beautified version from the Maps module, which is pretty convenient. So let's talk about doing some queries on the nav mesh. So if we run this, we're going to get some output. And we're going to be using some of these functions, and I'll describe what they are. So Navmesh Area, so how much total area is there on the nav mesh for the agent to navigate? This gives you some idea of kind of the size of the scene. And we can get this with navigable area property from the Pathfinder. Once again, we can also query the bounds if you want that bounding box. And we can also get random points off the nav mesh. So here we're asking the Pathfinder to give us one random point. We can seed the Pathfinder first, and then if you wanted to check other random points, you can check this seed and switch it up. So if we go look down at this map that we're generating, we're actually plotting these points. So this blue point is the random point we've drawn. What is this orange point? So here what we've actually done is we've asked what is the closest obstacle. So we've calculated this distance to closest obstacle using that nav point that we passed in and some search radius. And then at that point, we're asking for the hit record. We're saying, at that point, what is the normal and how far away is it? And then we're actually perturbing that point by the normal. So we're pushing it out of bounds. And then we're asking, well, if I have an out of bounds point, what is the closest point that's in bounds? And that's using the snap point method. Then we're grabbing that snapped point. We're verifying that it is navigable. So we'll look for this down in the output. And then we're going to plot that. And so here we're actually converting these visual points that we've appended to this list into top-down map coordinates and plotting them. So those visual points are the original nav point and the snapped point. So this orange point is that snapped point. And we can look through the outputs. We can see this is our original point. Is it navigable? Of course, because we sampled it. How big is the island radius? This is saying for this connected component of Navmesh, roughly how big is it? How far was this point we sampled to the boundary? And then at that point on the boundary, here's what that boundary point is. Here's the normal. Here's how far away that was. Here's the point once we projected it outside. And then is this point navigable? No, it's not. We can snap that back onto the nav mesh, so you can see we've modified it slightly to get it back on. Is that point navigable? Yes. And then we plotted that in orange. So go ahead and play with the seeds here, and maybe you can get some other output. So maybe, for example, we'll modify the seed once, and here's a new point. We can also do pathfinding queries directly on this nav mesh, and it's actually really easy. So we'll make sure our pathfinder is loaded. We'll set a seed. And then we'll grab 2 points off of the Navmesh at random with this getRandomNavigablePoint method. We'll initialize our instance of the shortest path object. And then we'll set the requested start and end to be our 2 samples that we just drew. Then we'll use the findPath function on the shortest path object that we created. And this is actually doing the pathfinding. And this will return a Boolean to let us know whether this was possible or not. Then it'll give us the geodesic distance of that path, so how long is the path, and then all of the points that belong on that path. And in here you can see we're printing this stuff out, so if we were to run this guy, we're waiting for it to compute. And then here we found our path. It's roughly 11 and maybe a third meter, and here are all the points that belong to it. And then we can display that with the maps module directly on this top-down map. So here's an indicator of the agent along the initial tangent direction of that path, and each of these points along this path is denoted here. We can also render out what the agent would actually see if it was standing at each of these points, looking down the next segment length. And that's what all of these renders are. So let's go up and just look real quick at how we plotted that. So here we're going to be grabbing the scene bounding box. We're going to be displaying this top-down map, doing the recolor, grabbing the grid dimensions, and then here for the entire trajectory, we're converting all of those points in 3D to points in 2D on the map using those grid dimensions. Then we're computing that initial tangent to set the agent and getting that orientation. Then once we have this top-down map, which we computed up here, we're just going to draw the path on it with the drawPath function, draw the agent on it with the drawAgent function, and then just display that with Matplotlib. And this section here is just going through each of those path points, computing the tangent, and setting up the agent and rendering those observations we see. Once again, we can play with the seed. And here you can see we have a brand new path in that same scene. So you can play with this a bit if you want to try generating paths in your environment. So those are some of the utilities. If we want to load a Navmesh for a scene, we can do so from File. Here I have this scenes directory where I have my GLB file and my Navmesh. If I dig into the files that are in this collab, you can see that in the data, scene data sets, habitat, test scenes, and here's this thing I'm pointing out. So anything you loaded up in here, you could load from here in the same cell. And essentially, when you initialize the habitat simulator, if there's a nav mesh present at the scene file that you specified, that's going to get loaded automatically. If there's not one, you can also load it manually with the load nav mesh function inside of Pathfinder. So you can always load any pre-computed nav mesh you have. We can also recompute this nav mesh during runtime, so we don't have to have one in advance. And I won't go into too much depth on all of these parameters, but I'll give you a little bit of an overview of the different parameters that we provide. There are voxelization parameters that are going to control that initial mesh to voxel conversion. There are agent parameters that allow you to parameterize the nav mesh itself based on your specific agent instance, so the agent's height and radius for that cylinder. Then there's the max climb and slope, and this will let you turn stairs or clutter on the ground into pathable and unpathable terrain. Some filtering options. We default all of these to true to kind of cull the nav mesh any places that would interfere with the agent. And then some detail mesh generation parameters that you probably won't need to modify very much. So in this cell, we actually have a working example of configuring the entire nav mesh and all the settings and then rebuilding it and visualizing it. So we'll play with this a little bit. First, if we turn off the use custom settings, then just run the cell. We're going to recompute the nav mesh for the scene with the default settings. So I can drive down here and see this is our nav mesh for the current scene. And here you can see it laid out. And I'm actually going to run this cell and load the apartment scene so we can see that too. So now we've run this in the apartment scene, and here we have, this is our agent position, looking into this room. This splotch is a couch that you can see here, and this is the table. And you can actually see the wireframe visualization of that nav mesh laid out here. And you can turn that wireframe visualization on and off using the nav mesh visualization property of the simulator. So just setting this to true or false will turn that on and off. All right, so what this code is doing is we're creating a nav mesh settings object. We're setting it to the defaults, and then if we turn on this custom settings flag, we'll consume all of these parameters that we're setting, and then simply recompute the nav mesh, and that's all you have to do. This section down here is just actually building a custom agent positioning. So all of these parameters here will allow you to either randomly generate an agent state from the seed, or to set your agent to a custom position and orientation. And if you toggle this try to make valid here, you'll actually do the snap point. So if you just set someplace that you think you want, it'll autocorrect. So here I'm setting 0, and I'm setting try to make valid. So when I run this guy, and we come down here, we can see that I successfully snapped that point to another position that's on the nav mesh that I didn't actually set. So this will just make it a little easier for you to try and position the agent in the scene. So with all of that said, let's maybe try some custom options. The first one I want to try is to do a kind of fat agent. So let's say your agent isn't just 0.1 meters, but it's actually 0.4 or 0.5 meters. Let's see. So let's make this 0.4 meters and then rerun this. So you'll notice now if we look into the scene and if we look at this top-down map that the area the agent can sit in is actually much smaller. So the agent's not going to fit into any of these skinny spaces, and it's actually not going to fit through doors either. So if we turn the camera to look at the door, we'll see that we actually can't fit through there anymore. So this is something you'll have to consider if your agent is going to be wider, that there are going to be areas that can't traverse. And these skinny areas are going to be really hard, especially for a discrete action space, for your agent to ever make it through. So these are kind of considerations to think about when you're finding which scenes will work well for your navigation. All right, so now let's try like the opposite. Let's do a really skinny agent. And let's actually make it pretty short too. So here, we're now 10 centimeters tall and 1 centimeter wide. So it's kind of like a pencil, right? So now you can see we're able to fit into much larger areas. Here we can even fit through all these side doors and openings. Let's turn the agent back to where we were looking at, because what's really interesting is, what about the tables? we would expect, like, I would think that a pencil would fit under this table. Clearly it fits here. Clearly it fits on top of this couch. But why not under this table? Well, it turns out that if we adjust our agent to be significantly different than the default, then the default voxelization is not going to be great either. So here we have a voxel width of 5 centimeters and a voxel height of 20 centimeters. So the voxels aren't even high enough resolution to find that area under the table. So let's adjust that. Let's make the voxel height half of our agent height and the voxel size to be about the same size as our agent, and then we will recompute this. Notice that it's taking a lot longer now because we're voxelizing with many more voxels. So this is something to consider if you're going to have to redo this often for your scenario. But as you can see here, let's expand this a little bit. We can actually fit in a lot more places in the scene, even inside of this flower pot, all over this table, under these tables, and on the windowsill. So this is clearly much more accurate, and you can see the same thing represented on this map. Note that there's only like half a meter of slack in the map. That's why this couch is still showing up as unpathable, because we're checking the scene minimum. So you're really not going to see this larger, kind of higher up part or the windowsills displayed here. That's just something to think about. Okay. So I suggest you play around with this stuff a little bit. Try it out. You can use this cell to generate nav meshes in advance for your agent. And maybe if I wanted to save this one to use it later so I didn't have to recompute it every time, I can do that here with the save nav mesh function. And then, clearly we can load that nav mesh anytime we want. So here I can click this, and I've just saved this version to disk. And so if you want to use these cells to generate your own nav meshes for your navigation trials, this could be a really great sandbox for you. Give it a try. For now, what I'm going to do is turn our custom settings off and recompute this nav mesh. So here we're back to the default settings. And I'm going to save this again, and we'll move on to actually using this nav mesh to do navigation. So in this section, we'll talk about taking actions on the nav mesh. And I want to bring up a little point here about sliding. So what exactly is sliding? Most game engines will allow an agent to slide along obstacles. So if you command a forward action into a wall, it'll allow you to slide. And this just makes it easier for players, easier for agents in the game. But we found that it actually hurts sim-to-real transfer. And if you're interested in more details about exactly how this works, I'd suggest reading up on this paper, Are We Making Real Progress in Simulated Environments? Measuring the sim-to-real gap in embodied visual navigation. And we did some sim-to-real correlation trials with and without sliding, and noticed that this is actually hurting performance if you try immediately applying these policies to real agents. So this is why we'll provide this option to turn it on and off. Note that turning it off will make it harder to train, but you'll get better performance when you go into the real world. So that's the caveat. And we're also going to talk a little bit about both discrete and continuous navigation in Habitat Sim. And we'll set this up. But first, what I want to do is I want to run this trial, run the cell here, and show you what's going to come out of it. So you see kind of what we're working towards, and then we'll build it. So here, our cell is outputting this. It's doing the simulation and displaying the video. And here's a video of the agent navigating in the scene using a continuous action space. And you'll notice that when it runs into the walls or objects, it kind of just keeps moving and keeps sliding. So this is the sliding case. Here, the agent is actually not able to slide, and so you're seeing that the agent hits this wall and then just is stuck there. And this is kind of what would happen if you commanded a real robot to just drive right into a wall. Okay, so let's look at actually setting this up now. We have this option in the cell to use the current scene. So if you want to go use that previous Navmesh recomputation function, you can then just check this box and it won't reload this new scene that we just reloaded. So you can try this on your own scenes. We also allow you to set the seed for where the agent will start and what random actions are drawn, and the simulation time that you want to simulate. Then you have a checkbox here for continuous or discrete navigation. So we can also recompute this whole trial with a discrete navigation policy. And then you can configure the control frequency and the frame skip for your continuous navigation case. And for the discrete navigation case, we're actually going to lock that down based on the actions we have configured to a control frequency of 3 actions per second with no frame skip, because we aren't doing any intermediate integration. No need to do that, it's going to waste time. So here's what that discrete navigation looks like. So if you're familiar with many of the standard point nav, this is kind of what that action space is going to look like. All right. So let's turn the continuous back on, and then let's look at setting this up. So we're loading our scene. We're then setting the control frequency. So we're going to do, for continuous nav, we're going to do 5 actions per second with 12 intermediate steps in between each action. So that's about 70 actions or 70 steps per second, where each step is an integration for that continuous velocity that we're setting. So knowing that we're going to have a certain number of actions over our horizon, we're going to pre-compute those. So that these 2 trials we show below, with and without sliding, use the same actions. Then we're going to set up this velocity control structure. Here's our velocity control. We can do linear and angular velocity, and we can set these to be local or global. Then for each of these 2 iterations, with and without sliding, the first one will be with sliding, the first one without. Then we'll go through, and for each time step that we just described above, we're going to do the control. So if we're doing continuous nav, we're going to set the linear and angular velocity off of this, these actions that we've pre-computed. If we're doing discrete, we're going to grab these out of our action space that we configured earlier. For discrete action space, we can use the body action to check collisions. So this is all kind of built in already. But I'll show you how to do this manually for continuous actions. Now, if we're doing continuous actions, we're going to first get the current state of the agent. Then we're going to use the velocity controls integrator to do an explicit Euler integration over our time step. And that's going to give us a new state, or at least a new target state. We're then going to use the step filter function to use the nav mesh to enforce the navigability constraints. And that's going to give us a new end position. Now, under the hood, this is applying the Pathfinder tri-step function, or the tri-step with no sliding. And you can go look at these. But essentially what these are doing that's more advanced than snap point is that we are actually enforcing that if you try and move through a wall, you're not going to be snapped to the other side of that wall. So you can go and dig into this a little more if you're interested in the details. We can then set that computed state directly back to the agent. And then we can check if a collision occurred by checking the distance we moved before and after the filter was applied, and then checking whether that distance was greater than some threshold. So we can kind of know whether the step filter had to apply something. And if it did, then clearly we hit an obstacle. We'll then run the simulation, if there's any simulation to do. And then we'll grab the frame. And at the end of all of this loop, we'll render out the video. And that's what we're seeing down here. So we can run this again. All right, and here's our navigation scene. So this is all of the basics for Habitat Sim and for the navigation and Navmesh section. We'll talk a little bit more about the Navmesh and the advanced features, specifically adding objects to the Navmesh dynamically that are not already in your scene, so go check that out if you're interested. And otherwise, thank you for watching this tutorial, and please play around with this collab environment we've set up. Maybe you'll find it useful for setting up your own scenarios.